Hi, James. We can see you.
Awesome, thank you. Is my audio okay too?
Yes.
Okay, perfect, thank you.
Yep. Let's just give it like one more minute for all the attendees to get let in. Sometimes it takes a minute. All right, let's get started. Hello, everybody. Welcome to the fourth and final day of the Sea Grant Marine Debris Symposium. I am so excited you're all here. My name is Maddie and I'm a Knaus Fellow in the National Sea Grant Office. A couple of reminders before we get started. Speakers, if you could please keep your video and microphone off until it is your turn to present so that we can all focus on the presentations, that would be great. As a reminder, these talks will be recorded and shared publicly, and talks are 10 minutes with 5 minutes for questions. And you can ask questions using the chat feature, which will look like this. One of these two, depending on if you're using the browser version or not of GoTo. So feel free to ask questions using the little question mark or the questions box. And I am now going to hand it over to Jennifer Lynch for her talk. Jennifer, go ahead.
Good morning and afternoon to many of you. On behalf of the other PIs from Hawaii Sea Grant and multiple sub-awardees, we really want to thank Congress and NOAA Sea Grant for this funding and the opportunity today to raise awareness about the large magnitude of marine debris in Hawaii. It took me a little while to get all my things situated on my screen here, so sorry for my awkward beginning. Our project's goal is to scale up removal by finding a long-term, large volume repurpose for it in local infrastructure. Next slide, please. This demands collaboration, something that Hawaii Pacific University's Center for Marine Debris Research prides itself on doing. This project is ambitious and complex, so much so that it requires a steering committee, currently with 26 members from all the organizations you see here and even more. The team includes the 4 most impactful marine debris removal organizations across the entire Hawaiian archipelago. Next slide. And here is our work location. The main Hawaiian Islands are encircled in yellow, and the northwestern Hawaiian Islands, or Papahanaumokuakea Marine National Monument, is in green. Because of our proximity to the largest and greatest concentration of aggregated floating plastic on the planet, called the Eastern North Pacific Garbage Patch, shown as that orange and red blob, Hawaii is among the most marine plastic polluted places on Earth. The majority of the marine debris here in Hawaii is derelict fishing gear of foreign origin. So prevention and behavioral changes efforts focused on local single-use plastic will do little to improve the situation. Efforts focused on foreign fishing industries and international food security will be the most impactful, but way more difficult. Next slide. Until those wicked problems are solved, there is much work to do cleaning up the nearly 100,000 tons of floating plastic in the Eastern North Pacific Garbage Patch. The nonprofit organizations in this project remove 200 metric tons per year. At this rate, and without more fishing gear lost into the ocean, it would take us 500 years to finish this big job. So each year we pull 200 tons from the ocean. But then what do we do with it? Next slide. This Sankey chart shows my best guesstimate of what we do with it. I suspect a significant portion of detected debris is actually left in the ocean. A lot of this stuff is really large and hard to remove. Of the debris that's removed, much of it is burned for electricity on Oahu, while a lot of the neighbor islands are using landfilling. Very small slivers of proportions are truly recycled. Next slide. To scale up removal and recycling, we must address each step in this process to find where the weaknesses are. We've identified 7 different steps, from detection to then dispatch and documentation, removal, transport, storage, sorting, and finally recycling, while research and education are needed at every single step. Organizations in the Hawaii Marine Debris Action Plan have laid the foundation for most of these steps. Now it's time to improve them and scale them up. The funding from Sea Grant is not equally distributed across these needs and does not satisfy the entire process. Nevertheless, we will use the funding in the most creative and efficient ways for the largest impact. In the next slides, I'll walk through our progress and plans for each one of these steps. Next slide. Nikolai Maximenko and Jan Hofner from the University of Hawaii, as part of our team, are developing a diagnostic drift model of floating debris. This model is estimating the location of the garbage patch in real time and using weather forecasts to predict which direction the debris may move. In August of 2023, just a few months ago, their model showed the patch had moved south and west closer to the Hawaiian Islands than it had been in the previous year. And sure enough, our removal of debris reflected the same thing. We saw an uptick in floats, nets, and other debris in September and October. This model is going to allow us to prepare for large pulses by shifting our attention from the other steps of the process back to detection and removal when the time is right. There are 3, next slide. Moving on to the reporting and documenting step. There are actually 3 or more systems available for the public and commercial fishermen in Hawaii to report large marine debris. 2 are run by the state and 1 is by our research center. Next slide. Our job in this project is to standardize the information that's collected from all 3 reporting mechanisms suggest more efficient dispatch communication options to the removal organizations, and collect information from each large marine debris event at all the 7 steps in the process into one centralized database. To accomplish this, we needed some help. So we are calling upon a really fun competition called the Hawaii Annual Code Challenge, which is currently happening right now. 6 teams of computer literate youth are competing to build the best dispatch and documentation database they can dream up. And the winners of this competition will be announced on November 18th. So hang tight for the results of that. I know we're looking forward to them. Next slide. The importance of such a cradle-to-grave database is that this Sankey chart can be created 3 years from now with accurate data, no more guesses. And in 3 years, our goal is that this chart will show very little debris left in the environment and more debris mechanically recycled. So next slide. Moving on to the removal step. This chart here shows the debris masses removed in pounds by our removal partners in this study. They're shown across the years, and the data is incomplete for the last few years. Before this talk, I was not able to gather all the information. A few things to point out on this chart is that the total amounts on the far right column are increasing through the years as effort has increased. PMDP and CMDR's efforts began more recently, and if you notice, PMDP is a rock star removal organization, removing more than 200 pounds per year from the northwestern Hawaiian Islands. This is amazing and hard work. If you add up the removal amounts in the main Hawaiian Islands, you see that the debris problem is on par with the northwestern Hawaiian Islands. The entire archipelago is impacted. The funding from the Sea Grant actually saved the removal operations in the main Hawaiian Islands. Much of their funding, which has come from the NOAA Marine Debris Program, expired in October of this year. So thank you very much. Next slide. Hawaii is a state of many islands, and no roads connect them. This means debris brought ashore on each island must be stored, transported, and handled on that island. This funding allowed us to secure storage nodes on Kauai, Maui, and Hawaii, and pay for cargo shipping of the debris from those neighbor islands to a hopeful centralized hub on Oahu. Next slide. And in that location, we hope to support or sort the debris by fishing gear type and polymer. And that's important because we want to be able to source the debris back to the responsible fishery for prevention strategies and to explore mechanical recycling opportunities, which the polymer information is very important for. Next slide. This shows a recently published study that we completed on what polymers make up the different fishing gear types that wash ashore on Oahu. So now we can visually sort out particular polymers from the piles of debris without the need of chemical polymer identification analysis. Next step, next slide. Excuse me, I'm getting over a cold. In this final step of the process, being recycling, unfortunately, the original funder pledging to establish this facility on Oahu has backed out. So we are seeking other funding sources to create a plastic recycling research facility that is large enough to receive 200 tons of marine debris per year, sort it, and convert it into products that are used for local infrastructure. A plastic waste conversion facility does not currently exist in Hawaii today. We hope to be the first one. Next slide. Research and education underpin everything that we're doing, and we have multiple universities involved in this project, including the Center for Marine Debris Research at Hawaii Pacific University, where we study megaplastics all the way down to nanoplastics. Last May, we graduated 5 master's students from the center, and hired them all. So we really are developing a workforce that is needed to address this urgent need. Next slide. In the project, we also have a program with the University of Hawaii Hilo on the Big Island, where they have a marine debris course in their marine science program. And this will give an opportunity for students from the Big Island to take this course, do an internship in marine debris research, and come over to Oahu to exchange information with us at CMDR. Next slide. And of course, we want to educate the public. And we do that wonderfully with a partnership with Hawaii Sea Grant that has TV shows and this beautiful magazine and other extension and outreach that they do. Next slide. I believe this is the last one, which comes straight from our proposal. We have an enormous problem. We are working creatively and towards the most impactful solutions, and the benefits and the more benefits are enormous. So thank you very much for your time, and I'll take questions.
Awesome. Thank you, Jennifer. That was so interesting to hear about. I loved it. What a multifaceted project. If anyone has questions, feel free to put them in the chat. In the meantime, I would love to know what surprised you the most about this project so far.
I'll focus on a happy surprise. I was surprised that Nikolai could pull together his diagnostic drift model so quickly. He really stepped up, I think even before funding was transferred to him, and was able to provide us some very fast numbers. And those
Awesome.
maps are just amazing. They're really allowing us to see what's happening out there in the pelagic zone that's threatening our coral reefs.
Oh, so cool, Jennifer. That's great to hear. Okay, wonderful. Well, thank you so much. That was so interesting. Such a great way to start off the day of talks. One thing I forgot to mention is all the talks today are challenge competition talks. So just for everyone's awareness. All right, thanks, Jennifer. We can move right along to Jill Murray talking about clean streets, clean seas, stormwater BMPs to intercept microplastics in urban runoff. Go ahead, Jill.
Okay, thanks, Maddie. You can go right to the next slide, actually, because this is such a collaborative project. And unlike a lot of the ones that I've seen so far, the talks that I've seen so far, this is a new project team, and it's really exciting. So I'm from the city of Santa Barbara. We have Patricia Holden from UCSB. We have Diana Lynn, Tony Hale, and Kelly Moran from the San Francisco Estuary Institute, Shelley Moore from the Moore Institute, Ted Von Bittner from WSP, Elizabeth Fassman-Beck from SCORP, Roger Sutherland and Ranger Kidwell Ross from Cascade Water Resources and worldsweeper.com. And from our Sea Grant team is Carla Eidelberg, Phyllis Griffman, Amalia Omada, and Karina Alvarez, and probably some new names soon as well. Next slide. So for those of you that are working on the larger plastics, microplastics become micro at 5 millimeters in size and smaller. Most of the microplastics in the environment are what we call secondary microplastics. They come from the breakdown of larger plastics, and plastics are everywhere, including the fishing debris that we just saw that great talk about. Okay, next slide. Microplastic is definitely a pollutant of, I would say, exponentially increasing concern. This is Google search in California for the last 15 years. And as microplastics were found in more and more environmental compartments, there started to be some legislation in California to address this. Then found in drinking water, it was an even bigger concern. California produced a California microplastic strategy in 2021, and then I updated the slide and saw once it was found in human blood, interest really increased. Okay, next slide. Here are some pictures of the main different types. On the left is the fragmented, the microplastic fragments that come from breakdown of larger solid items and litter. Then we have microfibers, which are coming from, and I think we're going to hear a really interesting talk about this later, come from breakdown of synthetic clothing and furniture materials, tarps, ropes, etc. And then a major concern as well is the breakdown of tires, and these are called tire wear particles. The rubber, ostensibly rubber tires contain many other compounds that make them become plastic particles and have chemicals that can be highly toxic to aquatic organisms. Next slide. So why microplastic interception, and that was one of the terms in the challenge competition, in stormwater is urgent. We know from work done by SFEI and others that in the coastal ocean, runoff from impervious surfaces, so streets, sidewalks, roofs, dominates transport to the coastal ocean. We know from some modeling of plastic production and currents and ecotoxicity that marine ecosystems will be harmed. It's not a matter of if, but when and where. And we also know that impervious surfaces are increasing as populations increase, and many of these are in sensitive watersheds with rapid discharge to the ocean. As we've been hearing from some of the talks, and we'll hear even more, long-term solutions are really the only way forward, such as product bans and producer responsibility, new products. And then also in California is really focusing on infiltration or using multi-benefit projects to soak rainwater into the ground and capture microplastic and other pollutants in those projects. We know from modeling in our municipality, which is fairly well built out, so we're not doing the large infiltration projects. We are looking at, we increase infiltration whenever a parcel, or we try whenever a parcel is redeveloped or remodeled. And so that is, we've projected out, 100 years before we're getting appreciable reduction in some of these pollutants, including microplastic and stormwater. And then we have the California trash amendments, which I'll talk more about, but they're targeting the trash that's larger than 5 millimeters, not the microplastic. So next slide. So the California trash amendments, it's a very ambitious goal, and it's 100% trash-free stormwater by 2030. And so that's 100% interception of trash that's on surfaces greater than 5 millimeters. There are two main paths to compliance. One is putting these, what they call full capture devices, inside storm drains, or maybe a net at the end of a storm drain before it discharges to a river or the ocean. And then track two is a combination of those type of devices plus things that are more like street sweeping and institutional control, outreach, product bans, and multi-benefit projects, which are more like the infiltration projects I discussed. This concerns me that because I work for a municipality, I know how expensive it is. I know what a big lift this is. It's for a very good cause, but are we missing a generational opportunity to address microplastic as we move forward with the trash amendments? Next slide. And here's what I'm referring to. So on the left is rain moving across an urban surface into a catch basin, which will then connect to storm drains and go on downstream untreated. But if we put the treatment, these full capture devices inside the catch basins, there's a schematic in the center panel, and you can see that the trash gets captured and the water goes through that filter and then goes to the storm drain. And then on the right is a photograph of what that could look like. What we don't know is if microplastic flows through these screens, and we don't know because the screens are generally about 5 millimeters, actually made to stop a cigarette butt. And we don't know if microplastic could actually be generated by tumbling the litter down inside the storm drain. It could be months before that litter is moved and could be jostled by multiple storms. Next slide. So we are trying to use public works activities for immediate microplastic interception while these longer term but more impactful solutions are hopefully finalized. So public works departments are in every municipality and county throughout the country, and some of their activities are regulated or at least strongly encouraged by their stormwater permits for that agency. The National Pollution Discharge and Elimination System permit, every municipality has one. They're called stormwater permits, and they are underlaid by the Clean Water Act. So most municipalities and public works departments are doing some kind of street sweeping and some kind of catch basin cleaning. And if so, can we reduce the loads of microplastic substantially by using these activities? And can we improve street sweeping to pick up even more microplastic? And as I referenced, do the full capture devices that most public works departments would be the group implementing, are they removing or generating microplastic? Next slide. So we put together a collaborative project, and there are some of the best scientists working on microplastic on this project. I feel incredibly fortunate. Our first objective is to determine quantitatively the ability of street sweeping to intercept microplastic and reduce stormwater loads. You know, it's one thing to know that you've captured some of it, but are you actually removing a measurable percent of what's getting into the ocean? And that's the city with UCSB. And then we're going to do an optimization project where we have simulated sediment and simulated microplastic added to that, spread it out in a very controlled environment, and have different street sweeper types and moving at different speeds with different amounts of, there's more details that we can get into to modify how they're moving through. Can they get even more microplastic that way? Next slide. And then SQUIRP is doing a controlled runoff study of street sweeping. They already had this project going. They have, they're looking at two sides of a street, one that's swept and one that's unswept, in a highly controlled simulated rainfall. They've devised a really accurate rainfall producing device. And we added microplastic to that project, so that we'll look at microplastic concentrations in the runoff from swept and unswept streets. And then SFEI, MORE, and WSP are going to evaluate the trash capture devices, and they'll have sampling. They'll collect samples upstream and downstream of runoff entering into and out of these catch basins with the devices in them. Next slide. We will look at catch basin cleaning. We'll see how much microplastic is in the sediment that's removed from catch basins, which most municipalities do on a somewhat regular basis. And then we'll synthesize the results. We hope to work with a student group at UCSB and produce a quantitative analysis of public works' ability to intercept microplastic between the time it's deposited on streets and discharges to the ocean. And we'll all be working on that. And throughout, we'll be engaging stormwater managers, public works groups, nonprofits, public audiences to maximize impact and the innovation of research. And we'll be doing, hopefully we'll be doing a competition to look at, we'll be looking at it's also a coding competition to try to develop an app that alerts people. One of the big problems with street sweeping apparently is people leaving their cars parked on the street. And if we can find a way to make that easier for people by getting an app where they can see when the street sweeper is 15 minutes away, they can go do a short errand instead of having to move their car all day. Next slide. I just wanted to share, in case anybody's wanting to add this research to this type of research to their projects. Quantifying microplastics is really difficult. First of all, we don't just go out and grab a sample like we would for chemistry or toxicity tests. We filter about up to 200 liters in the field, and that water gets pumped through a stack of sieves of different sizes, and then we deliver that whole set of stacks to the lab that's analyzing. So that takes a lot of time per sample, and here's some pictures of what some of that looks like in the microscope. Next slide. And then once it's sampled and sieved in the lab, those processes are really laborious as well. the microplastic is floated to the top and then filtered, and then there's microscopic analysis to characterize the different particles. And then there's what's called FTIR to look at the spectra, which identifies what type of polymer is present. So it's we really have to plan our sampling carefully because we don't have as many samples available as we would for more of like a chemistry type project. Okay, next slide. We've done a little bit of pilot work. We have found, quantified the microplastic in the city of and runoff from our creeks. We've gone and swept up by hand material on street surfaces before and after the street sweeper comes by, and that's what the two panels with the blue specks show. The upper one is before the street sweeper came by, and the bottom one is after. A couple of interesting things there. We knew there were some people doing gardening around there, and that blue really matches the exact color of weed whacker that you can go buy at a garden store. And then also the bottom panel shows that even though we picked up some street sweeping, because the top panel, the top panel was found in the street sweeper. That was street sweeper debris. And the bottom panel is what was left after the street sweeper came by. And so you can see there are smaller particles. There's still work to be done to pick up more of this. And this is a good time to point out that one really exciting part of this project is the jury is really truly out on whether street sweeping is going to be quantitatively helpful. Street sweeping is kind of underplayed in the California microplastic strategy, and that was because some studies have shown that fine particles are difficult to pick up. On the other hand, we have some of the biggest promoters of street sweeping on our project who have shown that street sweeping is by far the best bang for the buck when it comes to stormwater BMPs. And they suspect that since plastic particles are less dense, they should be picked up at even greater rates than sediment and associated contaminants. Okay, next slide. Our timeline is we're getting our project off the ground this year, dry weather sampling and convening our advisory groups. And then year 2 will be our big wet weather sampling push. And year 3 will be most of our data analysis and assimilation. And with that, I'll wrap up and take any questions.
Thank you, Jill. That was so interesting. If anyone has any questions for Jill, please feel free to put them in the chat. Jill, what would you say has been your biggest challenge so far?
The biggest challenge so far is, well, and I'm really speaking for the work that I'll be doing with UCSB, is getting microscope time, getting the time on the FTIR machine. That is, as more and more research is done on microplastic, the existing facilities are being more and more impacted. So we're looking at ways to add, the students working on this, we're driving about an hour south to get on an FTIR at Channel Islands, Cal State Channel Islands. We're trying to find ways to bring funding to UCSB to get the equipment there. The group that I'm working with is wonderful, so we haven't faced any challenges as a group yet.
That's awesome. You have another question. How do you best communicate about microplastic pollution to public audiences that may have bigger concerns like macroplastic pollution?
Well, I think the human health connection is probably a great motivator. I don't like to drive our outreach by fear, but this is reality. As you know, they're saying, well, we really don't know what the human health impacts are yet, but that's being studied. You know, as we're speaking, probably 10 papers are being published on this right now, and we're going to have a lot more information very soon. And so I think that ecosystem impact, just the way that the way some of the graphics with the turtle and the straw for the larger plastic and the albatross, the contents of the albatross's stomach. Once we have some really powerful graphic images and data, I think we'll be able to motivate people, the community.
Absolutely. All right. Thank you, Jill. That was wonderful. We can move right along to development of new detecting, cutting, and lifting technologies to increase efficiency to derelict fishing gear removal with James and possibly Kevin. Is Kevin joining
It's just
us?
today.
Okay, go ahead, James.
Aloha, everybody. My name is James Morioka. I represent the Papahanaumokuakea Marine Debris Project, or PMDP, and I'm here to present about our project in collaboration with Hawaii Sea Grant, the development of new detecting, cutting, and lifting technologies to increase operational efficiency to derelict fishing gear removal. I got a lot of pictures since we can't really share videos. So Madison, I want to need you to click away. Next slide, please. All right, so a little background about PMDP. We are a 501c3 nonprofit organization created to protect the sensitive wildlife and critical habitats of the Papahanaumokuakea Marine National Monument from the threats of marine debris. Next slide, please. And for those of you that may be unfamiliar with the Papahanaumokuakea Marine National Monument, it extends about 1,300 miles northwest of the 8 main inhabited Hawaiian Islands. It spans 1,300 miles, so if you were to stretch that across the continental US, it would reach from practically Las Vegas, Nevada, all the way to New Orleans, Louisiana. And the Northwestern Hawaiian Islands, or Papahanaumokuakea Marine National Monument, lies centrally in the world's largest ocean, the North Pacific Ocean, and also in the North Pacific Gyre, which is a system of oceanographic currents, from East Asia, the Aleutian Islands, the West Coast, all the way down to the equatorial, which moves a lot of water and subsequently moves a lot of marine debris from all over the North Pacific Ocean. Next slide, please. And so, although these islands are protected, there's no actual physical barrier which protects it from the threats of marine debris. We work across 7 different islands. So I guess working from the left side of your screen or the northwest side, Holaniku, Kuaihelani, Manawai, Kapo, Kamole, Kamokuokamohoali'i, and Lalo. Those are the 7 islands that we work at. And these 7 islands and atolls are estimated to accumulate about 115,000 pounds of marine debris annually. So about 57 tons. Next slide, please. And so truly an incredible place. It's home to more than 7,000 marine species of wildlife, 23 endangered species, 14 million seabirds, over 90% of the threatened Hawaiian green sea turtle population, about 75 to 80% of the endangered Hawaiian monk seal population, and 3.5 million acres of coral reefs, which makes up about 70% of the United States shallow water coral reef environments. Next slide, please. All right, so I just want to take you guys on a quick visual journey of what it's like to be in Papahanaumokuakea. This is an aerial shot of Manawai, which is your prototypical atoll. It's got a fringing reef, very low-lying small sand islets, and then an expansive area of shallow coral reef area, which makes up a footprint of where an old island used to be. Next slide, please. Could have really reticulated coral reefs, patch reefs areas, really expansive fringing reefs or back reef areas, low-lying small islets, expansive sand flats. Next slide, please. And tons of wildlife. They got the green sea turtles, the manta rays, schools of sharks, endangered Hawaiian monk seals. Next slide, please. Yeah, your school of coral reef fish, beautiful coral reefs. Like I said, the turtles. Next slide, please. Yeah, pods of spinner dolphins, schools of sharks, charismatic seabirds. And what you see there is a large tiger shark about 10 to 15 feet offshore about to eat a bird. So it's truly a very apex predator dominated ecosystem, very healthy, thriving ecosystem. And it's raw and pristine or near pristine and wild as nature is intended to be. Next slide, please. And, although it's really remote, it takes about 5 days by ship just to get to a lot of our work sites. And although it is protected by the federal government, there is no protection to, international marine debris. And so unfortunately, a lot of the shorelines or beaches look just like this, littered with domestic plastics and commercial fishing gear or derelict fishing gear. Next slide, please. And so a lot of this protected wildlife, or the wildlife that call this home, have to, live among this trash, this marine debris. Next slide, please. And the critically endangered monk seal is very curious, very charismatic, but loves to play with a lot of this entangling, threatening marine debris. Next slide. And beneath the ocean surface or the water surface, pretty much the same situation where it's decimated by derelict fishing gear, primarily derelict fishing nets. Next slide, please. And these are all pictures that we've taken in the field. So we've seen the wildlife interact and get entangled in this debris in the water. So you got your sharks, your turtles, your seals. Next slide. And it also happens on shore, unfortunately. Next slide, please. And then not only does it have, pose threats to wildlife, it has a lot of detrimental effects to the habitat. So right here, you see one of our divers peeling off an old derelict fishing net off of a once was living coral reef, and you can see it's just bare, exposed skeleton of where the coral once lived. Next slide, please. And so just a general process of how we, locate and remove the marine debris. We swim around or we get towed behind the small boats until we find this derelict fishing net in the water. We free dive down to the depths of the ocean's bottom to carefully cut this net off of the reef in small enough chunks to where our teams can either swim it to the boat or using pulling lines, manually haul it into the boat, and then everything is physically loaded into the deck of our small boat manually. Next slide, please. And so this is what it looks like after a successful mission. We spend about 2 one-month missions out at sea per year, and each 1-month mission can yield about 100,000 pounds of marine debris removed and about 1,000 acres of shallow coral reef area cleaned and restored. Next slide, please. And so PMDP, we're a relatively new organization. We got our first mission underway in 2020. And we removed 82,000 pounds. And in 2021, 2022, 2023, we've averaged 200,000 pounds over 60 days at sea. So about 100,000 pounds and 1,000 acres of coral reef area clean per 1-month mission. And in our short history, we removed about 716,000 pounds of marine debris. And so we're currently funded all the way through 2026 to do 60 days at sea. We're trying to scale up to do 90 days at sea so we can go beyond our 200,000 pounds. So we have future goals to remove more than 230,000 pounds of marine debris over the next 4 years. Next slide, please. And so I just wanted to introduce our project. We have other PIs here, Dr. Lerner, Dr. Okimoto, Kevin O'Brien, the president of PMDP, and we are funded through Sea Grant over the next 3 years. And this is something we're very excited about. This project got its start through NOAA Fisheries in the late 90s. Kevin and I both had the opportunity to work for NOAA Fisheries, so we're very familiar with the NOAA Marine Debris Program. Very grateful for all of your support, and we've been able to continue this project, but not much has changed in the methods, tools, or technologies to actually conduct the operations. So we're very excited. Next slide, please. So there's 3 main challenges or barriers to derelict fishing gear survey and removal operations, and that's 1, detecting the nets in water and on shores time and energy consumptive. 2, cutting these large masses of nets by hand is time consuming, tedious, and difficult. And 3, a lot of these large masses of DFG by lifting them by hand into a boat is time consuming, exhausting, and sometimes impossible. So a lot of these nets could be anywhere from about 800 pounds to about 4,000 pounds. The largest net we removed, a single piece, was 23,000 pounds, so 11.5 tons. And so these bottlenecks to DFG removal efficiency will result in higher operational costs and less total marine debris removed. Next slide, please. And so we want to tackle these 3 challenges in different ways. So currently our methods for surveying and detecting this in-water net is either by your traditional swim snorkel survey or being pulled behind a boat at 1 to 2 knots using tow boards. Our new innovative methods that we are going to implement this year are to use DPVs, or diver propulsion vehicles, or dive scooters, to help us with more rapid in-water surveys, and then also conducting aerial surveys using multispectral sensors. Next slide, please. The traditional way that we find these nets are we take spatial data, we digitize every single coral reef, we have historical points of where the nets were, and then as you can see in your bottom left picture, that's kind of the size and scale of what a coral reef looks like. And you can see even just with the RGB camera, you can kind of detect the green net right there in like the top half of that picture. And then on the bottom right picture is using near infrared. That's a net at the surface and how it pops using a different sensor. So we're very hopeful for using the multispectral sensor in real time to try and help find a lot of these marine debris hotspots or marine debris accumulation zones, so we can really yield greater removals. Next slide, please. And then cutting these large nets by hand is very difficult. And so right now, our methods involve us free diving, tensioning the net by hand, and cutting each net strand either with a dive knife or a bread knife. We also can use the small boat to kind of tension the net, so assisting the tensioning with the small boat and then cutting the net masses. But we hope to develop a tool, manual or electrical, which is capable of tensioning and cutting these large net masses underwater, since there is nothing currently available out on the market. Next slide, please. And then lifting these large masses by hand into a boat is very difficult. And so our current methods is to either swim the net or pull the net to the surface using pulling lines. But there are 3 sub-challenges which we'd like to identify, which is the deep, heavy nets are difficult to raise to the surface. And then the mechanical lifting devices like winches and davits cannot be mounted to our inflatable boats, which have to have really shallow draft, between 12 to 18 inches of draft, so we can really get into those really shallow water coral reefs. And then just straight up, some of these nets are too big for these small boats. Next slide, please. All right, so 1, deep heavy nets are difficult to raise to the surface. So we wanted to research and develop an inflatable lifting device capable of raising these large nets to the surface using like a system of lift bags, but also with integrated rigging so we can safely contain it and then tow this whole package back to the larger support vessel, which we use using our small boats. So these are just ideas of, sleds, kind of, that's a manta tow, but kind of something with like, an inflatable integrated system with wings that can kind of carry it over a lot of these shallow water reefs. Next slide, please. And then we developed a mechanical lifting apparatus like this A-frame for our inflatable small boats. So it's still a prototype. We're still going to try and improve, but it's something that can be mounted to the lifting points of these fully inflatable small boats, and we're able to par buckle a lot of these larger nets over the side. Next slide, please. And then lastly, we're going to develop a custom 19 to 25 foot heavy duty extraction platform with mechanical advantages like winches, davits, cranes, frames, A-frames, whatever it may be. So these are just ideas, using like landing crafts, davit arms. Ours will not be a boat like this. It'll just be an extraction platform. So something that we can build out at sea, be modular, and be able to tow to shallow water coral reefs to help us lift some of this debris. But these are just some ideas, and we're excited to get started. Next slide, please. All right, so these are the last couple slides. Our anticipated deliverables. Basically, we want to be able to share everything to the public. There's nothing commercially available for this type of, these types of tools and technologies. Not many places other than the Pacific Islands have to really deal with a lot of large derelict fishing nets on shallow water coral reefs. So first, we're going to, improve our detection using UAV imagery and DPVs. And obviously, we'd like to share all of those images publicly with everybody. If somebody can take that to the next level, we'd love to work with them. We want to make 1 optimized cutting tool prototype, 1 flotation and towing device prototype, 1 lifting apparatus prototype for the fully inflatable small boats, and then 1 prototype heavy-duty DFG extraction platform, and all designs will be made publicly available. Next slide, please. I didn't get to mention all of our partners. You know, our work is primarily funded by NIFWIF, the National Fish and Wildlife Foundation, which is supported by the No Marine Debris Program. So thank you guys for your support. Of course, Hawaii Sea Grant, we're very excited to get started. Since I was not able to share videos, I encourage you guys all to take out your phones, take a picture of the QR code on the right. There's a quick 9-minute video developed by Salesforce and Fortune Brand called Ecopreneurs, and it really gives us gives a great summary or overview of our project here at PMDP. And so that's all for me. My email is james@pmdphawaii.org. If you have any questions, feel free to reach out to me anytime. And thank you very much for tuning in.
Thanks, James. Thank you also for all those photos. They started out beautiful and they got very sad. Unsurprisingly, you got the question, how does one volunteer for this work?
Yeah, so we do not take volunteers out on our field mission. It is very intensive training. And so if you would like to, you know, dedicate 5 months to our organization, we do about 2 months of very rigorous, comprehensive training, which includes, you know, medical, the free diving aspect, small boat operations, our PMDP marine debris removal operations. We put it all together. We go out for a month. We try and remove over 100,000 pounds. We come back, we offload it, we dispose of the debris, rest our bodies for about 2 weeks, 1 to 2 weeks, and we get back out there and do it again, and then we demobilize for the project. But other than that, we're always looking for, you know, volunteers to help us with creative disposal alternatives or outreach and education. And so if you guys have any cool ideas or are interested, you guys are welcome to reach out to me at any time.
Thank you. And another question was, how long do you think it will take before some of the new technologies are commercially available and in wide use?
Yeah, so I mean, we have some deliverables over the next 3 years. We would like to make something almost, you know, near ready for the market by the end of the 3rd year. And so by the end of 2026, we'd at least like one optimized tool, whether that's an underwater reciprocating saw with the bread knife, or, you know, a band saw with a wire saw blade. You know, we're not really sure how often people will use it across the globe, but we hope that, you know, these products will make a difference, make a big splash out there for the consumers, because, you know, although we're a small organization taking care of a lot of coral reefs, we don't have the tools and technologies to do the project very well. And so we've been using the same methods for about 25 years. And we're very excited that now we have funding to advance that and hopefully be able to save more animals, remove more marine debris proactively, and, you know, save the planet one little step at a time. So thank you.
Thank you so much. That was really wonderful to hear about. All right, we can move on to the next talk. From blue-gray to blue-green, facilitating the transition to non-plastic natural material use in the coastal zone economy. Rob and Bill, go ahead. Oh, and Sarah, sorry.
Okay, I think everything's working now. Thank you, and I'm gonna take us through this a little bit quicker so we can try to get back on time. But I'm honestly still just excited about the last presentation. I am ready to go help James right now. That looks like some really important and awesome work. So I'm going to talk about our work on the coast of South Carolina that's coming together, focused on illuminating alternatives to plastics throughout the coastal zone. Next slide, please. So I see that we've got 2 big challenges here, and I think the first is better understanding the extent of this plastics problem, both physically and then the impacts that this has on us, ecosystems, and individual species. Secondarily, and just as important, is we can't wait for that first step to be complete before figuring out how we're going to move away from plastics in our economies. So we have focused with our project on that, on number 2, understanding that over time, we're only going to understand these impacts from plastics even more, and we can't wait to fully diagnose this plastics problem. Next slide, please. So paradoxically, I could say this because I am an environmental engineer, and we apply plastic all the time in the service of water quality protection or water quality improvement, and that's one part of our project. But this this paradox has somewhat catalyzed our entire project. In a parallel sense, we've seen how in aquaculture systems, plastics are common, from the buoys to the bags to the cages. Plastics are the most prevalent material, and in every setting, plastics are degrading, and they're releasing microplastics over time as they, photodegrade, are mechanically abraded, etc. So from my sector, I'm showing you 2 images here of a silt fencing material that was actually used not as a silt fence, but as a geotextile protecting a singular tree by a boat landing that we use on a relatively pristine property. We're here on Hobcob Barony in South Carolina to observe the environment as at a sentinel site. And so I'm, laying bare our shortcomings here. The next image to the right, is a causeway that was armored with plastics to hold that causeway in place. And that we're looking at just a few years of degradation over time, and that's releasing microplastics to a relatively pristine estuarine system that we've been working on monitoring for 50 years here. So potentially compromising science in a small way. So, this has been a blind spot. These are materials that are applied, especially in my domain, in the service of environmental protection, but they're leading to a different type of degradation. Next slide, please. So, and I apologize if this image had been presented earlier in one of the symposium presentations, but I find it amazing. On the right there, this is demonstrating the breakdown of commonly applied plastics as they're exposed to the really rough and tumble estuarine environment. So just after 8 weeks in situ, as you're moving from the leftmost column to the right, and you're seeing that pitting, that rugosity increasing radically, those are bits of microplastics being released to the environment. This helps explain why oftentimes, I know we probably experienced this earlier in our careers, in our lives, we might go to grab something that's plastic and appears to be intact, that's been out there in the environment, weathering over time, and it just kind of shatters in our hand. And that's because at this microscopic scale, there is this intense degradation. And this is what we have most especially, with our estuarine environments, where you have alternating wetting and drying, sandblasting, hurricanes, et cetera. Everything that you could throw at a material is essentially here and active in the South Carolina estuarine environment. Next slide, please. So for our project, we're going to focus on 3 broad sectors in the coastal zone. So water quality protection, so things like silt fences, silt socks, geotextiles to protect from erosion and nutrient additions to water bodies, to coastal aquaculture, focusing on primarily oystering, which is a growth area in coastal South Carolina, and restoration, so living shorelines, and often that's where we're kind of smearing between aquaculture and environmental restoration, because some of that also pertains to just reef restoration, especially in our coastal zone. but can also entail, say, creek bank restoration, shoreline restoration, etc. Next slide, please. So we've already identified some non-plastic material options that are out there commercially. Again, they're produced on a small scale. Oftentimes these are more expensive, but in some cases, as in the relatively broadly applied geotextiles that are entirely organic, such as burlap, jute, coir. We do have large-scale and competitively priced products that we can prove work well enough in the coastal zone. But things from myco buoys to the various iterations of reef prisms and the different shapes that have been demonstrated down in Florida, we're excited to port that to South Carolina. Next, please. So our approach is starting with stakeholders, identifying needs, moving through materials testing, which Bob will tell us about in just a few minutes, small scale and then larger scale field deployments, and all the while checking on the economic feasibility of the options that we're pursuing. And this is a partnership between Clemson, USC, University of Dayton, South Carolina Sea Grant, and a private consulting firm, Robinson Design Engineers. Next, please. And so I'm going to pass it on to Sarah Pettigo with South Carolina Sea Grant to take us through this next step.
Thank you, Bill. And yes, I'm going to share briefly on stakeholder engagement. So for this project, we've assembled an advisory council of experts within each of the three sectors mentioned, so water quality, environmental restoration, and aquaculture. And this is just so that we can better understand where and how to focus our efforts. And so as a key start to this work, we convened an initial workshop for this advisory council in October, and this was in Georgetown, South Carolina. And so for a recap of this workshop, some points of discussion during the day were, first off, identifying potential items for replacement with biodegradable alternatives, and then also identifying end users and deliverables for applying these findings. And so to add an additional benefit of having this workshop in person, bringing this advisory council of experts and the project team together was just to create this forum for communication, getting to know one another, so that we really can work well together and have some great benefits from this research. And so tentatively, the council will have an official meeting each year of the project, and we're going to have iterative feedback and engagement continually during this as well. So next slide, please. So I'll also talk briefly on extension efforts for this project. And so you're about to hear from Bob that for this work, we're going to test materials at the lab scale, mesocosm scale, and the field scale. And so for the field testing component, Sea Grant specialists are going to facilitate connections with local stakeholders to be able to gain some feedback on the materials that are evaluated. And so one example of this, as a shellfish aquaculture specialist, I'll be able to work with growers and facilitate those connections to be able to test some materials on mariculture sites and in their operations to gather feedback from them. And this is really just being able to apply what we learned. And then second, we are also going to be working throughout the project to engage stakeholders as well as our expert advisory council to vet the list of deliverables that we originally proposed for this work. And we're doing this for a couple different reasons. First off, to make sure that we are targeting the right end users. And then second, to ensure that the materials and information pathways are created and shared in a way that they're received. And a quick note here, this was actually one of the main takeaways from the advisory council meeting that we had in October, that this process of making sure that we're identifying the people that need this and making sure they can have this information in a way that's usable to them, it's going to be an iterative approach. So we're looking forward to engaging readily with our stakeholders and with our advisory council to extend these results essentially. And then lastly, we are creating a project web page for the advisory council as well as everyone to keep up with project updates and progress along the way. And so this QR code right now is just a holding page, but you can look forward to more information about the project there. And that is all. So Bob, I will pass it over to you.
Thanks, Sarah. Yeah, next slide, please. I think Bill did a good job of setting this up here, but one of the overarching ideas here is we do want to move from plastics that are used in these three different sectors here: aquaculture, shoreline restoration, and water quality protection, to natural alternatives. So I guess a good example are these geotextiles you see here at left, often made of HDPE, high density polyethylene, polypropylene, polyurethane, you name it. We've talked about, I think, pretty extensively how when it breaks down, that's not great across multiple levels. So we're interested in natural alternatives. So some of the ones that have been identified are jute, coir, wattle, and so on. So of course, one thematic question that arises that Bill alluded to is before we can adopt these materials, they have to be qualified for integrity, ability to survive in these harsh environments of coastal South Carolina. Next slide, please. So sort of getting at that central thematic question, we want to expose these materials to not just environmental conditioning, but application relevant environmental conditioning. So factors of interest, I think, depending on the application, include things like temperature, moisture, ultraviolet light, salt, and then abrasion due to sand. So there's sort of two legs of this environmental conditioning. The first leg you see at the left there are sort of what we would call laboratory scale exposures, which literally are going to be performed on equipment in the lab. So at left you see a temperature and humidity chamber there that's able to expose materials to a pretty broad range of temperatures and humidities. And then at the right in that box at the left, we see a UV chamber where we can control things like irradiance and thus heat flux or light flux onto specimens. So what this really allows us to do at the end of the day is decouple factors. So instead of having everything confounded together, we can isolate things like temperature, isolate things like humidity, and have very careful control over them. Goals from that, first of all, we can hopefully accelerate weathering so we can very quickly and rapidly qualify materials. So laboratory allows you to accelerate exposures. You can do things in much shorter time scales than would happen in the environment and figure out what's going to occur in terms of degradation. Secondly, I think another nice thing is it does maybe lend some insight. If we can decouple factors, we can figure out where maybe appropriate use cases are. Maybe a material is very resistant to temperature cycling, but it is relatively crappy at being photooxidative. It doesn't do well when it's exposed to light. So that would inform maybe where we can use certain materials. So I think that's a useful thing. And maybe also once we isolate and identify what's driving degradation, perhaps then we can come up with responsible engineering strategies to reinforce these materials, to treat their surfaces, to mitigate degradation. So I think that's kind of where that's going. Second leg is more of the mesocosm and field exposure pathway. So this sort of involves small scale pilot testing. This will include controlled environmental testing using Baruch's indoor climate controlled lab. There's also several sites near Baruch that's spread over its estuarine system to allow us to get some different environmental factors that are going to allow us to sort of confirm what we suspected in terms of how they're going to perform. This will evolve into full scale field scale pilot testing, as Sarah mentioned, in collaboration with our coastal partners. All right, so that next slide. So that's kind of how we're going to expose these materials to the environment. Then the question is, well, how do they degrade? How do we quantify and qualify how they degrade in a sort of a numeric kind of way? So our plan is to perform mechanical testing in the lab. So you can see this machine here at the left. This lives at UD. We use this thing a lot here in my group. So what we're thinking of doing, for example, is cutting, you might imagine like a square swatch of burlap. And we're going to grip those specimens, just like this. You can sort of see in that picture at left there, that little blow up, you can see there's a little dog bone in there. Well, we'll insert a swatch in there, we'll pull on it in this thing called a universal testing machine. And the idea is the machine will measure how much force the specimen is feeling and how much it's elongating during this deformation history. So we'll be able to calculate 3 properties, hopefully, from that data. Modulus, which is a measure of stiffness, how resistant is the material to being deformed. Strength, how much load can it take before it breaks, and then elongation at break is just how much did it stretch before it snaps. So what we want to do then is compare these degraded properties to virgin properties, and that'll give us sort of a normalized metric for how well the degraded materials did relative to the virgin materials. So that's kind of our rough plan for performing this testing and quantifying how much did these environmental factors degrade the material. Yep, next slide. Yeah, I guess that's it. I thought there might be something else. Bill told me I was going to wrap up and close out, so questions?
Thank you, guys. That was wonderful. We are actually at time, so we do need to motor on, but that was great. Thank you so much. All right. Now for our final, is this our final? Yes, this is our last talk of the Sea Grant Marine Debris Symposium, which is wild. Last but not least, we have developing sustainable and closed loop solutions to reduce synthetic fibers, microplastics, and nanoplastics leakage from laundry systems into the marine environment. Nick, go ahead.
Thank you very much. I take it you can hear me okay, so that's great. Well, thank you, everybody. Thank you for coming today. What an amazing set of talks. And I think the last group who are talking about basically plastic alternatives, that's the right way to go eventually. The world is not quite there yet, but that's definitely the future, which is great. So I'm going to talk about developing solutions to reducing the number of synthetic fibers, such as microplastics and nanoplastics, that actually come from our laundry systems and get into the oceans as a consequence. And not many of you, me included, actually probably know most about that. But basically, you wash a lot of your clothes. We have a lot of plastics in our clothes, and they get out into the grey water, the water that's flushed away from the washing machine, and then they get out into the ecosystem. But before we're getting onto that, I'd just like to thank Dr. Bejan Yan, lead PI on this program at our end at Columbia University, and all our collaborators there that you can see at Columbia, Stony Brook University, North Carolina State University, Karen and Ben, and obviously our sponsors at the New York Sea Grants. Thank you very much. Next slide, please. Thank you. So basically, what is the problem? Well, the problem is that microplastics don't go away. They kind of just get smaller. And so they, as one of the other talkers mentioned, they just degrade and they degrade. And so we're talking about microplastics, but they eventually get all the way down to being nanoplastics. And at nanoplastic level, they are really, really tiny. And we don't know quite what effect that might have on the biological systems. We're a biological system, so as well. So they can go, when they're down to the nanoplastic level, you can get, we think that they can get through, like the blood-brain barriers or any of the blood membrane barriers. And so it's a little scary to think that we probably have plastics in our brains. I can't tell that I've noticed, but who knows? And people are studying that. So to get the microplastics and the plastics out of our environment is such a key thing. And I think NOAA is well into that and well ahead of the game with the funding, the different things that they're funding here. There's various places. Obviously, the plastics get into the rivers, they get into the oceans, they come off runoff. And I think Jill Murray in an earlier talk was talking about plastics being washed down the drains and then straight into the sea. And she had a question actually, which was it Clean Streets, I think, her talk. And it was whether the devices they were putting into drains, which are amazing things to catch all this stuff that gets down there, stop it getting out into the ocean. would they stop microplastics? And I think it's highly likely that they probably wouldn't. And Jill, we should talk more about that. So thank you, Noah, for bringing us all together, because if the work that we're doing progresses how we think it's going, maybe we can help on that level as well. Let's go on to the next slide. So the title of this talk and where we're going is actually largely related to microplastics coming from our clothes. And so our lab has now turned into a laundrette, which is great. I get all my washing done for free. And then we test it all, which is a bit scary. And we see that there's lots of fibers coming off all our clothes. And I think there's a little at the bottom of the screen, you can see it says there's more than 1 million micro nanoplastics released from just washing 10 pounds of polyester clothes, which is a phenomenal amount. And they just get washed straight down the drain. They go through every filter system that is almost certainly out there right now, and straight out into the rivers through the storm drains and out into the ocean, and then back into the biological systems as the food chain starts to ingest them, and then we pick them up eventually. So it's something that we need to do a lot of work on, and we're looking to see if we can remove them at source, this source at least. There are other sources, but this seems to be quite a major contributor. And it started out for us when Dr. Joachim Goes at Columbia University took a group of students around Manhattan. You can go around Manhattan in a boat. I'm in New York, by the way, for those that didn't know it. And they were testing water for all sorts of biological things. And they noticed that there's blooms of microplastics at very specific places that were persisting around the island. And when they looked at it, they're out at the outlet of storm drains. So again, it's back to Jill Murray's kind of talk on what goes down the storm drain goes straight out into the rivers and the oceans. And following the storm drains back up, they discovered that particularly in somewhere as built up as Manhattan, a lot of the buildings have laundries in the basement. So there's just big laundries all over the place there anyway. And they're all washing their grey water down into the drains. And those are causing the blooms. And that's really the thing that started us thinking about this work. Next slide, please. So specifically, what we're trying to do with the help of NOAA is develop a very highly efficient and fast filtration system, and inexpensive and low energy. With any luck, almost no energy. In other words, it'll be passive in the system, but there is probably some work we have to do on that. But this is all part of the development. We aim to remove the majority of microplastics and eventually nanoplastics, which is actually a little bit more difficult, from commercial and residential washers and dryers. And then we will take that prototype of a system that we develop, which we think is going to be very commercializable, and take it to the laundry industry, and hope that, we think they will probably take it up because they're all very interested in that. And we would like to take it to government and talk about policy and making sure that the people who make the policy understand that the type of filtering that we need to do to get rid of these tiny, tiny particles is probably an order of magnitude more than what they're thinking right now. And so this is where we're going to go with this. So we want to, it says, validate the demonstrated filtration systems. So in other words, we're going to test different filtration methods. We already have a different way of looking at it, which we think is actually already starting to show some really promising signs, which is really great. And then we want to ensure that they're feasible in this real world setting, meaning they can be used day to day, day in, day out, in like a laundry, something like that. And then as part of this, we're going to generate a lot of plastic filaments in a mat almost that come out of the side of the filter, if you like. And as part of like this circular economy that we're all attempting to be in, I think at the moment, it'd be really nice if we can recycle and reuse these collected microplastics. And we're talking to industrial partners with the sort of a view to doing that. And really what that means is wherever we put our filters, we'll collect a lot of these microplastics into this kind of goo. We can dry out. It's full of fibers at that point. We can give those to these companies, which some of you may have already heard about, who I saw one on the TV yesterday. I got a huge grant for basically tearing apart plastics and then rebuilding them into fibers and reusing them. And so you can actually remake clothes from the fibers that you can recover like this. And that's something where we can pass our filter outputs to them. It'd be fantastic to be able to do that and reduce the amount of new plastics that we need to make, if at all, once we get to the alternative. And we also, we're a teaching university, but it's a great thing to do anyway, in that we include a lot of education in and outreach into all our work. And so we want to get in there at the grassroots level. And the kids are the ones who are so engaged in all this. It is amazing. And if we can go to the next slide, please. So we've been showing them how simple some of these processes are in the lab, always more difficult to scale up. But in the middle of this picture, you can see a little funnel, and then there's a pipe, and there's a little blue thing, which is a filter. And literally under gravity, you can pour in water, like in the glass on the right, which has like a red label on it. And that's stuff that came out of a washing machine, classic grey water. And you pour it, and just let gravity pour it down through that filter, and it separates basically the water particles out from the water particles, the water molecules from the filtered particles. Hard to say that. And you can actually get very good results, and the water that comes out of it is actually very clean and drinkable, I would say, which is fantastic. Next slide, please. So, as you've been hearing, we're trying to get to this idea of a circular economy where we can maybe talk to the washing machine manufacturers, get them to include filters that we develop under this program, install them into things like large laundry outfits. We can take the fibers from that and we can incorporate them into the areas where people are reprocessing fibers of microplastic for reuse, which is amazing. They can sometimes, if they can make thread from that, they can feed it back to the fashion industry. The fashion industry remake clothes with them, which is stunning in itself. And we keep the kids, the K-12, all school kids. I'm a school kid, so school kids up to 95. I'm not quite 95. All like to know about this stuff because it's very new to nearly everybody. And the more we can teach people about it, the more knowledgeable they are, the more they can help to reduce and alleviate the problem. And then feed that into the policymakers. Thank you. Next one. So we recently had at the Columbia University, at the Lamont Observatory, which is a Earth Research Institute at the university, we had an open house. It was the rainiest day ever, I think there. It was unreal, but we still had about 2,000 people came. And the tent, which you can see in the top right corner of this image, which was largely handed over to talking about the things I've just been talking about, microplastics, where you find them, how you can even understand what they are, and where we're going to try and alleviate the problem of them. It was packed all the time in that tent. It was just amazing to see how engaged the public was. Next slide, please. And so we're so grateful that the NOAA Marine Debris Program, the Sea Grants folks have been helping us to start this up because we couldn't have done it without them. We're right next to the Hudson River in New York, which is a huge river that is well used by thousands of people a day, and they're very keen and interested in participating in what we're doing. Columbia Climate School are very supportive of us for obvious reasons, and the Hudson River Keepers, they're volunteer people who keep an eye on the river and try to keep it as healthy as possible. So they are very keen on everything that we're doing. So this is fantastic. Next slide, please. Oh, was that the last one?
Yeah, I think that was the last one.
So I could talk about all this all day. It's such a fascinating subject. I don't really need slides, by the way. I just keep talking.
That was great. Thank you so much.
Has anybody, would you have any questions?
I don't see any right now. What has been your favorite part of working on this project?
My favorite part, I think it's just the fact that I knew so little about it. I'm an engineer in a kind of high-tech world, and so I spent a lot of time with sensors, deploying them in the field and things, as we're an Earth science sort of institution. But getting involved with this particular program, I've suddenly realized just how pervasive microplastics are across our whole environment, in our bodies. You know, they're already there. Oh, there is something. We just literally sent a whole set of equipment to some people who are going to ski to the South Pole. Yeah, they're going to go from the coast to the South Pole, and it's taken them 50 days to get there, and it's going to be horrendous conditions, as you can imagine. They're at the South Pole. It's minus 50 degrees and all this sort of stuff. But they wanted to do something for the environment, and we all thought that a good thing to do was for them to take snow samples from the coast, where there's a few people, to the South Pole, where there's actually quite a lot of people in a building, basically, surprisingly, and then in between, where there's almost no one. And look at how microplastics have even maybe pervaded that environment, which is about as far as from anywhere you can get on the planet. So that's going to be so informative, and they're literally off in 2 weeks.
Wow, that is wild. I'm excited to hear what they find. All right, thank you, Nick. That was wonderful. Thank you so much for that final talk.
Thank you for having me, by the way.
Thank you, thank you. And I just would love to take a minute to thank, there are a few people that made this whole symposium possible. I want to thank my steering committee, which consisted of Amy Gories, Amara Davis, Tanya Torres, and Jill Bartolotta, and a handful of CNOWS fellows who have been so graciously facilitating the breakout sessions last Thursday, and we'll do it again today. So I just want to thank everybody so much for coming. It's been such a joy to hear from all of our grantees on all the great work that they're doing. And for all of our grantees, I just want to remind you that we have breakout sessions today from 4 to 5 p.m. So I'll see all of you there. But thank you so much, everyone. This has been so wonderful. Thanks, and I hope you have a great holiday weekend.